All right, so the plan for today is just to continue with sections 2.3 and 2.4. Still just working on building up to solving more general equations. Um, so solving equations with constants and variables on both sides, and then developing a general strategy and getting a little bit of practice with it. The quote of the day for today is to make strategic use of the learning curve, with kind of a related idea about different types of knowledge. So what's kind of the idea behind this? Well, there's a couple different ways you can think of a learning curve, but the way that I think about it, I know we haven't quite gotten to graphing yet, but I think most of us have kind of seen graphs, at least like of the stock market or something like that. Or I think of a graph like this when I look at, say, time or effort invested versus, let's say, something like expertise or something along those lines. Uh, so you can, with kind of a moderate investment of time or effort, you can develop a reasonable level of expertise in maybe some some specific field. Um, so obviously, part of your schooling is that you want to be able to go deep into at least one topic. You want to be kind of over here, but that takes really an enormous amount of time and effort. There's a diminishing marginal return for a time and effort, right? Uh, if I'm taking a really advanced course to learn a really advanced concept, I might have to spend, 100 hours just to master, that little concept or that idea, where at the more beginning stages, I can master concepts a little more quickly. So uh, I think, some folks focus too much on going super deep into one specific topic because they really like that topic. And then they find out that they don't really have the breadth to handle a lot of different situations. And some folks go the opposite way. They have a huge breadth. They, kind of take all of the courses they catch their eye, but never really dig into one topic really deeply. So for instance, with like some, degrees like general business degree or a general communications degree, that can be a danger if you're not careful. So I think kind of planning it out so that, across a field, you have, you know, most areas where you have a bit of expertise, and then, you have a couple areas where you can go really deep. Um, and trying to minimize the places where you might have essentially zero expertise. If nothing else, if you're on an interview or something and the interviewer asks you a question that's kind of related to one of your areas of expertise, but a little bit in a different field, then you'll at least have some grounding to be able to answer that or address it knowledgeably. So, take advantage of the fact that you can gain knowledge and expertise fairly rapidly at the beginning of study, and you can study a lot of different things. And kind of a couple caveats here. One is that, beware of the Dunning-Kruger effect. Don't think that because you put 100 hours of effort into something that you're now an expert in it. That's certainly not the case, and that's not what I mean to imply here. Um, and you know, a moderate amount of time looks something like maybe around 300 hours. So this could be like an hour a day every day for a year, more or less, or an hour a day a few times a week for 2 years, something like that, studying some topic, some field. Um, so that's what I mean by something along the lines of a moderate amount of time or effort. Basically, something like roughly equivalent to 2 college level classes, something like that. And you'll be, pretty uh, fluent at least in that topic. And the other thing I think about when I'm thinking about what would I like to spend my kind of educational time and effort on, this is a little bit different than fun or leisure activity. Although, they can certainly overlap. I like to think of knowledge in kind of 4 quadrants split up by 2 different factors. One is uh, time constant. So if I learn a thing, how long is it useful for before that piece of knowledge is no longer useful? Is it dynamic or is it more static? Right? If I learn this piece of information or how to do this thing and 6 months later it's not worth anything anymore, that's a fairly dynamic system. It's changing very rapidly. That means I have to spend a lot of time just refreshing the knowledge that I already had so that it doesn't go away. And then also, what type of knowledge is it? Is it trivial or foundational? A trivial piece of knowledge is almost like an island, kind of like isolated from everything else. I can't really build much off of that. If I learn this piece of knowledge, it doesn't, make it easier for me to learn the next piece of knowledge. And it doesn't really tie into a whole lot. Versus something more foundational. If I learn this concept, then I can learn a more advanced concept that builds on it, and a more advanced concept that builds on that, and so on. Or maybe a more foundational piece of knowledge tends to tie into and relate to a lot more things that you know. Um, so, personally, I like this quadrant, obviously, being a math person. I like when I learn something, it doesn't change, and I like to learn things that I can then build off of. But that's not to say that that's, the best quadrant or anything like that. That's my personal preference. But there are people who, are up here in this quadrant that I don't like, but these are like tech support folks. These are the people who, every time that Microsoft Office comes up with an update and, something changes and I don't know how to do it and I get frustrated, I call somebody up and they've put in the time and effort to learn all of the new stuff and keep their knowledge base up to date, to act as a reference for me. So, that it's not my favorite quadrant, but it's some people's favorite quadrant, um, and that's valuable as well. But just thinking about the costs and benefits, the trade-offs of the different quadrants of knowledge. Okay, so that is the kind of quote and thought for today. So last time we had discussed a little bit about two-step or multi-step equations. And now we're going to move into more general equations. So here we're still dealing with uh, just linear equations where we have variable terms, number times variable, and constant terms. And in this case, on both sides. So both expressions that are being equated have both a variable term and a constant term. So just to be a little more explicit about that, we have a variable term here on the left side and a variable term here on the right side, the 3a and the 10a. And we have a constant term on the left side, this -1. And we have a constant term on the right side, the +5. And remember, our goal is to get the variable isolated, the variable itself isolated. And the intermediate step to that was to get the variable term isolated. So I want to work my way towards number times a, times my variable here is the letter a, equals some other number, and then I can get a equals my answer. To isolate my variable term, I need to get all my variable terms on one side of the equation and all of the non-variable terms, all of the constant terms on the other side of the equation. And for the time being, we're going to do this in two different steps. When you get more used to it, you might choose to do these two operations in one step, and that's perfectly fine. But we're going to do it in two steps for the time being. Okay, so if I look at my variable terms, the first thing that I'm going to try to do is to get my a's together, basically. If I look at my equation overall right now, I see that I have a's in two different places. Everything is simplified, right? That kind of is uh, a prerequisite piece of work to doing this set of steps. But everything is simplified. On the left side, there's nothing I can distribute or no like terms I can combine, anything like that. And same on the right side. But I still see that I have two variable terms. I need to combine them together. Now I could move the 10a from the right to the left side by doing something like subtracting 10a from both sides. And this wouldn't be the end of the world. You can definitely do this, but we kind of mentioned last time, well, on the left, if I have 3a minus 10a, that's a negative 7a. And whenever I have extra minuses or negatives floating around, it's at least for me, it's more likely I'm going to make a mistake, that I'm going to leave that negative off, or maybe later on when we talk about inequalities, that if I multiply or divide by a negative, I might forget to flip the inequality. So my preference is going to be to move the 3a. If I subtract 3a from both sides, then on the left side over here, I have 3a minus 3a, they go away. And on the left side, I'm left with negative 1. That's equal to, and on the right side, I have 10a minus 3a is 7a plus 5. So I look at my equation now, and I only have one variable term, the 7a, across my whole equation. So I've gotten my variable terms all combined together under a single variable term. Again, it has the nice benefit here that the coefficient is a positive number, but not the end of the world if you did it the other way and you had a negative 7a on the left side. Again, that, you can still proceed forward. That's not wrong or incorrect or anything. Just maybe a slightly more error prone. Just be careful with that negative sign and you'll be fine. But I've got my single variable term now. And now my goal is to isolate that variable term. To get that variable term by itself, I want 7a equals number. That 7a has a plus 5 attached to it. And of course, I move the 5 by subtracting 5 from both sides of the equation. Always remember the most important, the most important aspect of any of these equation solving steps is if I do something to one side, I have to do it to the other side. Think of my scales, right? If I take 5, kilograms off of one side of the scale, I've got to take 5 off the other side of the scale so it remains in balance. And again, my right side, 7a plus 5 minus 5 goes away. On my left side, negative 1 minus 5. Be a little careful with the direction of the subtraction and so on, but that is negative 6. I've now successfully isolated the variable term. I've got number times a equals number. And now to work on isolating the variable itself, well, this 7a, there's a coefficient of 7 multiplying the a. I want the a completely by itself. I just divide by that coefficient of 7. On the right side, I have 7 times a divided by 7, or that's just 7 divided by 7 times a, or 1 times a, or just a on the right side. And on the left side, I just have negative 6 divided by 7, or the fraction negative 6/7. So after simplifying all of the, any like terms or anything like that, combining any like terms and distributing anything, that kind of thing, this is kind of the most general form of a linear equation, where I have a variable term and a constant term on both sides of the equal sign. So there's a sense in which this is like as complicated as it gets. Now there might be some details. Maybe there's a fraction as one of the coefficients or a decimal as one of the constant terms that can make it maybe a little more challenging, say, as far as the arithmetic goes. But conceptually speaking, having a variable term and a constant term on both sides of the equation is kind of as simple as it can get after we've made all the simplifications to each expression on each side of the equation. So the nice thing is that if we understand this structure, if we understand our different goals, our different intermediate goals, we combine the variable terms, we isolate the variable term, we isolate the variable itself. And then, of course, always kind of hidden in the background is we check our work, we plug back in. Again, you know, I only every once in a while check the answer in class if I'm trying to demonstrate something, but you know, I want to focus class time on the new concepts and not checking our work so much, but checking your work is a good idea, a very good idea um, for certainly for the exams, also for homeworks, or just when you're doing work on your own. So if we understand this structure, combine the variable terms together on one side of the equation, isolate the variable term by getting the constant terms combined together on the other side of the equation, isolate the variable itself by dividing through by the coefficient. That's really the strategy, the kind of, you know, overview of how to solve any linear equation like this. Okay, let's look at another example down here. So 5x plus 7 equals 12x minus 8. Let me actually zoom this in a little bit. There we go. So 5x plus 7 equals 12x minus 8. So again, I note that each expression individually, 5x plus 7, 12x minus 8, there's no simplification to be done. Can't combine any like terms, can't distribute anything out, nothing like that. Okay, so I'm going to proceed forward with my strategy from up here. I see that I have two variable terms across this equation. There's the 5x term on the left side, the 12x on the right side. I'm going to combine those together on one side. And again, if I subtract the 12x, kind of thinking a step ahead, 5x minus 12x is going to give me a negative coefficient. Not the end of the world, but I'd rather go the other direction and subtract 5x from both sides. So we have 5x minus 5x, they go away. We're left with 7 on the left-hand side. And 12x minus 5x is 7x minus 8. I have now combined my variable terms. I look across my entire equation and I only see now a single variable term. So I made some progress. I want to isolate my variable term. I want this 7x by itself. Right now it has a minus 8 attached to it. I get rid of that by adding 8. And if I do it to one side, better do it to the other side as well. So I have on my right side 7x minus 8 plus 8, they go away. On the left side, 7 plus 8 is 15. I've now isolated my variable term. This 7x is over here by itself. There's no other constant term attached to it. All of the constants are on the left-hand side, all of the constant terms. And now I have number times x equals number. I divide by the coefficient. I divide by 7. And I get x equals 15/7, which, as always, I would typically outside of class, I would plug back in and double check. Okay, so I think I will put this general strategy up here along with these two exercises. So the general strategy is we simplify and combine like terms and so on if we need to. We won't need to in either of these two exercises, but in future ones we may need to. We get the variable terms on one side and the constants on the other side and simplify. So we combine variable terms, then isolate the variable term. We divide by the coefficient to get the solution. We isolate the variable itself, and then we check the solution. So I have two equations here to be solved. Why don't you take about 6 minutes to, let's say 5 minutes to solve these two. I think 5 minutes should be good because we don't have to do a whole lot of simplification or anything. But take about 5 minutes, and as usual, I will write a few notes as we go along in case you get stuck anywhere, but we'll touch base in 5 minutes. And if you have questions, you can just pop them in the chat. Otherwise, in 5 minutes, we'll go over these solutions. Okay, it is just about 5 minutes. So let's take a look at these two. So for the first one, again, we have this kind of same setup. We have variable term and constant term on both sides, and there's really nothing that we can simplify in either of the expressions on either of the sides of the equation independently. 7a minus 1 or 15a plus 4 already in simplest form. I want to get my variable terms together, combine my variable terms, and I'll choose to subtract 7a from both sides. So I have 15a minus 7a is 8a on the right, and then it's plus 4 in the -1 just comes down. So I have -1 equals 8a plus 4. I've combined my variable terms. Now I want to work towards isolating my variable term, getting that 8a by itself. It has a plus 4 attached to it at the moment, so I just subtract 4 from both sides. Leave me with 8a on the right, and -1 minus 4 is -5 on the left. I've now isolated my variable term. I have number times a equals number, and I've got one more step to get my solution. I have a coefficient of 8 attached to my a, my variable. I just divide both sides by 8. 8a over 8 just leaves me with a. And on the left, I have -5 divided by 8 is -5/8. I've isolated the variable and gotten the solution. And then last, I checked the solution, and I did that over here as a demonstration. So plugging back into the original equation, 7 times -5/8 minus 1 on the left, and 15 times -5/8 plus 4 on the right, are those two equal? And if we multiply out, get a common denominator everywhere, just make this -1 into -8/8, and this 4 into 32/8. Yeah, could you add one first? You could. There is some flexibility with these steps. I think roughly speaking, I don't think I'm making a mistake saying this. If you take these 3 steps, I think you could do them in any order that you want. If I don't know, there might have to be a caveat there, but more or less you could do the 3 steps in any order you want. But but I think this way of approaching it is usually the most straightforward. But yeah, if you combine the constant terms first, I don't think that's a problem. The downside of that is if you combine the constant terms on one side, if you're not looking a couple steps ahead, then when you combine your variable terms on the other side, you might end up with a negative coefficient on your variable. It's a little harder to predict. Um, you'd have to think of that ahead of time. Um, and again, it's not the end of the world if you end up with a negative coefficient on your single variable term. You just have to take a little more care, slightly more care at this point, and in some future sections, a little bit more care. So when we have inequalities, when you multiply or divide by a negative, you have to flip the inequality, and that's just one more thing to remember, one more place that you can make an error. So, um, I prefer this order of doing things, this approach, but could you do the steps in a different order? Um, yeah, but as long as you're careful. Okay, so getting everything over 8, then we can just multiply everything through by 8, get rid of the denominator, the 8, and really we're asking, is it true that -35 minus 8 equals -75 plus 32? And that is true. -43 equals -43, so we've checked our answer. For the second one, again, very similar setup. We'll subtract 5x from both sides, giving me 7 equals 11x minus 9. That combines my variable terms together. Then we'll work on isolating the variable term by adding 9 to both sides to get 11x equals 16. We now have our variable term on one side, our constant term on the other side. We're ready to isolate the variable itself by dividing by the coefficient, dividing by 11. And we get x equals 16 over 11 as the answer. And again, ideally, we'd go and check this. But for the sake of time in the class, we won't worry about checking this one. Any questions on these two exercises? So especially if you were going through the last step in checking, 5 minutes was um, was a challenging amount of time to get these completed in. So if you didn't get all the way through, that's perfectly okay. Um, or if you got stuck somewhere and had to, look up and take a look at, oh wait, what do I do next? That's perfectly fine. So don't, get down on yourself if um, the time was a little bit short, or if you, struggled somewhere. That's the point of these exercises, is to kind of work through some of that, and um, maybe to identify weaknesses if you have a weakness. If you say, oh yeah, I think I got this down, but then you struggle a little bit on the exercises, maybe that's a topic that warrants a little bit more practice or drilling later on. So do, make notes like that in your notes as well, aside from just the math. Did you struggle on this one? Did you feel good on this one? Maybe you have a shorthand like a check if I felt good about it, a question mark if I want to come back to it and review that topic, something like that. Okay, let's look at one more example here. And let me move this up to a little closer to the general strategy here. So what if we have decimals or fractions involved? Well, there are some shortcuts we can take that we'll see later on, but we can take essentially the same approach. I see I have, let me bump this away from that line so I can notate this. I see I have a variable term on each side and a constant term on each side. And my same strategy should work just fine. I start by trying to combine my variable terms together. My variable here is W. On the right-hand side, I have 1.1W minus 1.1W. They go away, and plus 10 left over. Just because I have decimal coefficients, or if I had decimal constant terms, or fraction coefficients, or fraction constant terms, it doesn't really change anything. The arithmetic works the same as above. 2.6W minus 1.1W. What's 2.6 minus 1.1? That is 1.5 W minus 50. So I've now combined my variable terms together. I would like to work on isolating my variable term, getting this 1.5W by itself. It has a minus 50 on it right now. I'll add 50 to both sides. And I have 1.5W equals 60 on the right side. I've isolated my variable term. And now I want to isolate the variable itself. I divide by 1.5. So I have W equals 60 divided by 1.5. I probably want to simplify this answer. And I might remember from Math 80 or from previous work that I can, in the numerator and denominator, move the decimal point one place to the right or left, or two places or three places, as long as I do it to both the top and the bottom. So 60 is 60.0 and 1.5 on the bottom. I move both of those decimal points one place to the right to give me 600 divided by 15. Well, I see that there's a factor of 5 in both of those, I think. I think 3 times 5 is 15. And, well, 5 times 20 is 100. So 5 times 20 times 6 should be 600. My 5's divide out. And I see that there's a factor of 3 in the 6. I'll just be very explicit and write it clearly. 6 breaks into 2 times 3. And my 3's divide out. 20 times 2 is 40. So W equals 40 is my answer. I could have gotten a decimal or fraction is my answer, that could have been possible as well. In this case, I got an integer. Okay, so I'd like to take a few minutes here, maybe actually about 8 or 9 minutes, and do something called a Cornell Notes exercise. Now, I don't think this exercise is going to be super helpful for this particular problem. And the reason is that I've kind of almost done it for you here in this general strategy. So if you need kind of a hint as to what to do, take a look back at this general strategy. But this is the idea of a Cornell Notes exercise. We're kind of doing this one almost half as a practice and half as an exercise. But you can take this to, all of the future problems that we do in the course or in other courses. And the idea is take a look at an example that was done in lecture. So say this one, for instance, that we just did. Okay, this is kind of a slightly new ball game. We have some decimal coefficients. How do we have to deal with those? You have the mathematical steps that I went through to solve the equation. Presumably you copied those down in your notes and you have that series of steps. Maybe ideally, I probably should not have there, not have pushed that off to the side. Well, I actually need a little more room. Down below when I say off to the right side would make a little bit more sense if I had everything lined up. There we go. Get rid of that as well. Okay. So now when we say off to the right, it makes a little more sense. Off to the right, describe each step in your own words. So I went from here to here, write out words, not math symbols, not numbers, but in words, what did I do? So something like combine the variable terms together, maybe something like that. From here to here, I did a step. Write out words here, as one phrase or maybe a sentence, something like that. What did I do here? Right? I isolated the variable term. Now, I mean, when you go through and do this, your wording is probably not going to be as polished as mine. I mean, I've, read textbooks on I've seen how a lot of textbook authors describe this, and I've thought through it myself. And when you're seeing it the first time, your wording might be a little more awkward or something. That's fine. It's just something that prompts you to say, okay, at a more foundational level, more abstract level, what's going on here? So do that for each of these steps. Writing out words over here, right? So again, this might be something like combine the variable terms, for example. And then take a new question, a new problem, a new equation in this case, that looks pretty similar, and write your steps down. So copy these blue steps down off to the right. Right, so copy your steps over here. And then use those steps to help you work through the math. Try to actually go through and solve this problem. Now, I will give you a little heads up. There's a little bit of a hiccup here. I threw a little bit of a hiccup in. You might see it right away. But there is something that's a little different in this problem than the previous one, to where maybe this exact set of verbal steps isn't going to work perfectly, but can we maybe adapt that system to this problem to make it work, right? Is there maybe something else that we could do? And again, if you need to, you might want to look back at the general strategy for a little bit of insight. but that's the Cornell notes exercise. So in this previous example, the one we just did, in your actual notes, do this yourself. Um, write verbal descriptions of each step that was done. Write those next to this, copy down this new equation in your notes, write those kind of off to the right, those verbal descriptions, and then try to use those to help you, to help kind of guide your strategy for solving this new equation. And I'm going to try to get everything on screen here. So I think I can erase this just for the time being. I'm going to bump this statement here down a little bit and copy this general strategy now. There. So everything is on screen now. So take maybe about 8 minutes or so and go through this. It does take a little bit of time, but I think it's good to go through this exercise because again, this exercise isn't intended to be just for this problem, but really it's intended to show you a method that you can use for any problem, any new type of problem we come across for the rest of the course and even in other courses. So take about 8 minutes, work through this Cornell notes exercise, and then we'll come back and we'll go through it. Okay, it's just about 8 minutes, so let's work back through this. So hopefully you were able to get through everything. Um, I did give a little more time on this problem so that you have time to write down the steps, and also as you kind of saw as I was going along, um, maybe I realized that I would like to say add a step in, maybe to remind myself to simplify at the end. Maybe that's something that I would like to note. Um, or maybe I want to flesh out a little bit, uh, combine the variable terms, preferring to keep the coefficient positive. Maybe I want to add a little bit more as I'm going along, and I kind of remember maybe I went to move the 2.9 and I say, oh, wait, no, I think I want to go the other way, right? So as I'm going through a problem, maybe that even feeds back into the system and I flesh out my instructions a little bit. I don't want, a paragraph for each of the instructions. So there is a little bit of a balancing act here. I want enough to remind me of the crucial step, what to do next, but not so much that it just ends up being like reading a book. Uh, I did notice that, up above, I started with combining the variable terms, but that didn't work so nicely here because this 2.9 was multiplied by parentheses W plus 40. That was actually something I didn't see in the previous problem or even the previous few problems. We kind of started right away with each of our expressions in simplest form, so I might have not really thought about that. But I come up to this new problem and I say, okay, I kind of want to start with combining variable terms, but I can't start there. What went wrong? Am I just applying completely the wrong strategy? Well, no, I think this is still within that ballpark of just a linear equation with constants and variables on both sides. But oh, wait, maybe I want to simplify both sides first. I remember we did that at some point in the past. Let me add that into my narrative description on the right side here. So leave yourself some nice bit of room, right, in case you need to add anything in along the way. So I distribute and simplify, and I end up with a right-hand side that looks like 2.9W plus 116. Now I have everything in simplest form. I can proceed forward with my original kind of blue instructions taken from the previous example. I can combine my variable terms, preferring to keep the coefficient positive. So I'll subtract 1.7W from both sides to get negative 20 equals 1.2W. Got my variable term combined now. Plus 116. So I look across my equation, I only have one variable term now anywhere. I then want to isolate the variable term by moving the constant term. This plus 116 is attached to the 1.2W. Get that on the other side. I'll subtract 116 from both sides, leaving me with 1.2W equals negative 136. I've now successfully isolated the variable term. I've got my 1.2W all by itself. And then I can isolate the variable or get the solution. And maybe I remind myself I do this by dividing by the coefficient of the variable, in this case 1.2. So divide both sides by 1.2, and I end up with W equals negative 136 over 1.2. And then maybe something I may have forgotten to write down up here. Maybe I forgot to include a verbal step to simplify, right? Maybe I didn't write that down, but so maybe I add that in. Again, as this is a process that kind of goes both ways. As I'm looking for inspiration on what mathematical step to do next, I read my verbal cues, but also maybe I realize that in this particular problem, something else has come up, or maybe there's a note that I would like to have that I didn't write down from the previous problem, and maybe I add that note in. And the nice thing is you can then take these notes and kind of combine them into a strategy. And you can write them next to every problem, and they give you just kind of a verbal cue of what the strategy looks like. Okay. So I'm a little confused when multiplying 2.9 by 40, it's not 11.6. Yeah, so good question. So at kind of a basic level, we know that 2.9 is about 3, and 40 times 3 is about 120. So I think, 4 times 2.9 would be 11.6, but 40 times 2.9 should be over 100. Um, so we can kind of just see just with the orders of magnitude that we've got to be more like 116 than 11.6. But my guess would be, so if you did 2.9 times, say, 4.0, if you put a point there, that could be, it could be like an entry error in the calculator. Um, or if you were doing multiplication by hand, um, one thing that could happen is if you forgot to bring down your zero. So if you did like 9 fours are 36 and put your 6 here, 4 times 2 is 8, plus 3 is 11, and then move the decimal point one place. So what do we forget to do here if we were doing this by hand? Well, we forgot to bring down the 0 from the 40 first, and then the 9 times 4 is 36, 4 times 2 is 8, 11, and now we move the decimal point one place. So I think maybe it might have been one of those two, depending on whether um, worked it out by hand or calculator. You might have put a decimal point in there, or you might have forgot to kind of bring down that 0. That would be my guess. Um, but that does bring up a good point that, when we're doing a computation like this, we always want to have in the back of our mind about what we want the answer to be, right? So I look at this and I say that's about 3 times 40, which I know is about 120. So I should end up with an answer 100-ish, right? If I get 11.6, or if I got like 1,160, I would know that something went wrong somewhere. Uh, so I hope that that clarifies things a little bit. But yeah, so we then work to isolate the variable term, subtracting 116 from both sides. We isolated the variable. We got down here, and then we said, okay, yeah, we need to simplify. Again, maybe we put another verbal cue in for that. Maybe you say to yourself, oh, okay, I always know to simplify things at the end, so maybe I don't need to be reminded of that, right? It's um, there's not, one correct answer for this. It's a question of what works for you. What cues do you want to give yourself? Um, and then just going through the 136 over 1.2, I just pulled the negative off and just brought it over here to the side to do some scratch work to work out what that is. Um, and sometimes doing things like this, 1,000 plus 360 over 2 times 6, I can divide the 1,000 by 2 and the 360 by 2 separately. That makes it a little more manageable, a little easier to think about. So that's 500 plus 180 over 6. Or that's 500 plus 180 over 2 times 3, and I can divide each of these by 2. That's 250 and 90 over 3, or that's where I got negative 340 over 3, or negative 113 and a third. So this was, I think, not an easy problem, but hopefully with the practice that we've had so far, along with this kind of Cornell notes strategy, hopefully that made this manageable. If it wasn't manageable, if it was really a struggle for you, if you really didn't get it, um, not a big deal. We're learning this at this point. This isn't the point in the course where you're supposed to have mastered this material. So if you really did struggle with this, well, practice on the homework, drill some problems. Uh, that's perfectly fine to be at that point in the course. But I would, remember this Cornell notes exercise and use it throughout the course, particularly if you come across a topic or a type of problem that you're struggling with a little bit, going through your class notes and doing this exercise, coming up with a verbal description of the strategy. can help a lot. Okay. So let's move toward a general strategy to solve linear equations. I know that I kind of wrote a general strategy here, but our goal is going to be where's my general strategy? Well, our goal is going to be just to get a little more practice. Let me actually copy this down. Going to be to get a little more practice using this strategy. I thought I had another copy of this down here, but there we go. Okay, and we kind of saw from up above that we had looked at some simpler examples where we didn't have to do simplification at the beginning, but we maybe want to add in this step one here, simplify, combine like terms. We want to get each side of the equation, each expression as simple as possible before we start doing any equation solving steps. We want to kind of get to this, what we might call standard form, where we have a single variable term and a single constant term at most on both sides. There can be times when maybe, I don't have this variable term or I don't have this constant term or something, that's fine. But we don't want to have multiple variable terms or multiple constant terms or things with parentheses or anything like that on either side. So here I see my right side is nice and simplified. I have one constant term, one variable term, but my left-hand side, it's a little bit of a mess. It kind of looks like I have like two constant terms. I've got a distributive property going on here, a fraction multiplying parentheses. So I want to work on this left side. That's the first thing I'm going to do. I'm going to take this left-hand side and I'm going to simplify it. So I'm just going to bring this left-hand side off to the side so I don't have to write the equals right-hand side every time. That's just going to get cumbersome. And honestly, if the more times I have to copy the same thing down, I might just make a transcription error. I might just mistakenly copy a minus as a plus or something, or copy a two as or the four and the two backwards or something like that. So the less that I have to copy things down, that's also a benefit. So if it's not a benefit for me to copy it down, then why take the extra time and the chance of making an error? Right? It's like the telephone game that I think everybody has played, right? The more times you copy something down, just the more chance there is to make a silly error. But let me take this fraction, 3/4, this coefficient, and distribute it to the binomial, this 4m minus 8. That all comes from this bit here, and then a plus 7 at the end. All right, 3/4 times 4. Well, my 4s divide out. That's just 3/4 times 4 over 1, right? Or 3 times 4 divided by 4. This just gives me 3m minus 3/4 times 8. Again, that's 3 times 8 over 4, or, well, the factor of 4 and the 8 divides out, gives me 3 times 2, or 6. My 3m, my variable term, it doesn't have any other like terms in this expression, nothing to combine with. But my minus 6 plus 7 can combine to make a plus 1. My left-hand side that looks so complicated up here, it simplifies down to just 3m plus 1. So maybe a green, I'll kind of go back up and rephrase this as 3m plus 1 equals, and I'll write 4 minus 2m. Now, as a little aside, I could certainly write equals negative 2m plus 4. There's absolutely nothing wrong with that. That's perfectly good math. And frankly, that's a perfectly good way to write it too. The reason I tend to not do this when I have the option is, well, if I write equals negative 2m, if I'm being a little sloppy, I might end up with something like that, right? If I'm writing a little quickly on an exam or something like that, and and it's easy for that negative sign to get kind of lost in the shuffle, right? It's easy for me to just not be able to see that negative sign clearly if I'm writing a little bit sloppy and reading a little bit quickly. Eh, if I can help it, I would like I would prefer my minus signs to be between two terms. It just makes the minus sign pop a little more. Again, this is a very uh, minor detail. And certainly if your handwriting is nicer than mine, then maybe you don't have this problem. Um, but I try to do everything that I can with these just little things to reduce my chances of making an error on each step. I have a bunch of these little rules that I tend to follow. It's not the end of the world if I don't follow them, right? Like I tend to like to put my variable terms on the side that gives me a positive coefficient. So I'm just a little less likely to uh, make an error with a negative. But if I come up with, 10 different little ways of reducing the chance of making an error, and, if I was making an error once every five problems, say 20% of the time, and I can reduce that to making an error like these kind of silly errors, say 5% of the time, well, imagine if you're on an exam and instead of losing 20 percentage points, you only lose 5 percentage points. Instead of going down 2 letter grades, you only get on a half a letter grade from kind of silly mistakes, so to speak. The kind of mistakes that you look at it and you read back through your notes and you're like, oh, I can't believe I did that, right? Not the kind of mistakes where you're like, okay, I really don't understand uh, this topic. So, just being good at not making these errors, coming up with little things that help you with that, um, is, you know, is a way to boost your grade in math. So just a little side note on that. And I would say, that's a good strategy for a lot of different things, right? If you can just come up with little ways of doing things that reduce your chance of making an error, right? When you're sending emails, if you're sending a professional email, like write your email and don't put the person's email address in until you're ready to click send. So you don't just mistakenly send the email when it's half written. Just little things like that that can, that aren't the kind of thing that's going to get you fired or something, or but it just makes life a little bit easier, makes things flow a little bit better. Okay, but at this point I have each side simplified. I have a variable term and a constant term on each side of the equation. So I've kind of got one checked off here. I've got everything simplified, combined, etc. I'm in this kind of standard form. Uh, I wouldn't worry too much about this A bigger than or equal to C kind of deal. Uh, you know, at least not at this point. Next, I want to combine my variable terms together. And again, I could subtract 3m from both sides to do that, but that would give me a negative coefficient, and I'd rather avoid that, so I'll choose to add 2m to both sides. If I did subtract 3m, not the end of the world. I could still certainly solve the equation and would probably still get it right, just a tiny bit more error prone. On the right side, 4 minus 2m plus 2m is just 4. 3m plus 2m gives me 5m plus 1. Okay, I've combined my variable terms. I now want to work on isolating my variable term. Subtract 1 from both sides to get 5m equals 3. I have now isolated my variable term, and I want to isolate the variable itself by dividing by the coefficient. And ideally, I would go and check, but we will move on from here unless there are any questions. Okay, so as an exercise, uh, take maybe about 3 minutes or so, work through this problem. It's quite similar in nature to the previous one. Work through this problem. We'll come back in 3 minutes and touch base. Okay, let's take a look at this solution. So again, like the previous one, we have a right-hand side that's nice and simplified already, but the left-hand side could use some work. So we distribute the 2/3 into the 6m minus 9 to get 2/3 times 6m minus 2/3 times 9, and then the plus 5 just comes along to the next line. So 2/3 times 6m, we could think about this as 2 times 6 over 3m, and the factor of 3 in the bottom divides out the factor of 3 and the 6 in the top, give me 2 times 2 or 4m. Similarly with the 2/3 times 9, the factor of 3 in the denominator divides out one of the factors of 3 in the 9, leaving another. 2 times 3 is 6 after the minus sign. So we have 4m, the only variable term, and the minus 6 plus 5. Those two constant terms can combine to make a minus 1. So our left-hand side boils down to just 4m minus 1, and then that's equal to 4 minus 5m. That was already simplified, so we didn't need to do anything else there. And now we're ready to go. We want to combine our variable terms together. We'll choose to do that by adding 5m to both sides. That gets rid of the 5m off the right and gives us a 9m on the left side. You can tell I'm going a little more quickly now. We've gone through several of these examples, and this is kind of our second day dealing uh, with solving equations. So I am picking up the pace a little bit. But if you have questions, stop me and I'm happy to answer. We isolate a variable term by adding 1 to both sides, giving me 9m equals 5. And then we isolate the variable itself by dividing by the coefficient 9, to get m equals 5/9. Any questions on that one? Okay, what about something like this one? In this case, actually, both the left-hand side and the right-hand side are kind of a mess. So I'm going to work with both of them independently. If you want to, you can even have, you could have colored pencils to do your scratch work if you want. They usually don't erase super nicely, so one little caveat to that, but sometimes using different colors can help keep different ideas separated. So I'll do the left side in blue and the right side maybe in green, and then kind of bring them back together in black, for instance. So I'll work with my left side by itself. I see I want to distribute the 5 through. That gives me 10x minus 5 plus 7, or that's 10x plus 2 on the left side. The right side, I can distribute the 2, giving me 2x plus 2 times 3, or plus 6, plus 8x, and I see I now have 2 variable terms that can combine together to give me 10x plus 6. And I might notice something interesting happened here. 10x plus 2 equals 10x plus 6. You might notice the problem right away, or if we go through, if we go through our equation solving steps, I subtract 10x off one side, do the same thing to the other side, and unfortunately, or maybe not unfortunately, but it turns out that I get rid of all of my x's. I just get 2 equals 6. What the heck does that mean? I think for time constraints, we are going to jump down to this next topic. So let's think about this a little more deeply. So when I'm looking at an equation, again, what am I kind of imagining as a setup? I have like a scale as a balance with, in this case, a plate on one side that has 4 little, coins on it or something. I have a plate on the left side that has 1 coin, and it has an envelope with some number of coins in it on that left side as well, and the scales balance. Or I have this mathematical expression, x plus 1, where x represents some number. I have this other expression, just the very simple expression, the number 4, and I'm claiming those two are equal. They represent the same mathematical quantity. When I say solve the equation, really what I mean is find the value or values of x that make the equation true. In this case, x equals 3 is the one and only solution. We call this a conditional equation. In other words, this equation is true if and only if we meet the condition that the value we substitute in for x is 3. If I put in if I put in 10 for x, or if I put in negative 5/4 for x, I'm not going to get a correct equation. The truth of this equation, the truth of this statement is conditioned on the criterion that x equals 3. The only way this is true is if x equals 3. Now, if I come down here and I look at something like x plus 1 equals x plus 4, if I say, okay, I have two envelopes, and I know that they contain exactly the same number of coins, I put them on the scale, they balance, right? One envelope on the left side, one envelope on the right side, it balances. Now I put one coin extra on the left side and 4 coins extra on the right side. The right side's always going to go down. The envelope is the same, and the right side picks up 4 coins and the left picks up only one. The right side's going to be heavier. Can x plus 1 ever equal x plus 4? Well, no. If I try x equals 0, I get supposedly 1 equals 4. That's certainly not true. Or if I pick x equals 10, maybe that's a solution. 11 equals 14. That's not true. This is always false for every x. There's no x that makes this equation here true. If I try to apply an equation solving step, I mean, this looks like my nice, just standard form of a linear equation. I should be able to subtract x from both sides to try to combine the variable terms, and I get 1 equals 4. And I see, of course, 1 equals 4 is always a false statement. 1 is not equal to 4. Okay. Let's just think a little more differently, or a little bit more deeply about, I'm going to look for a kind of cleaner example up here, about this sequence of steps here. I have this equation. I applied an equation solving step and got this one. I applied another equation solving step and got this one. And I applied another and got this equation. I mean, it's the answer, but it's still kind of just a trivially solvable equation. What's the purpose of these equation solving steps? The purpose is to get a new equation that's simpler, that's kind of a step toward this kind of simplest possible equation. And importantly, that has exactly the same solutions as the previous one. When I apply valid equation solving steps, like say subtracting a variable term from both sides or subtracting a constant from both sides, things like that, those are valid equation solving steps. They're allowed. When I do those, I get another equation that might look a little different, but it has exactly the same solutions as the previous equation. Now let's jump back down here, all the way down here. I applied a valid equation solving step to this one. I subtracted x from both sides. That is allowed. I got another equation, 1 equals 4, that has exactly the same solutions. Is there any value of x that I can choose that would make 1 equal to 4? Of course not. That's almost so silly of a question that it almost doesn't make sense. If I change the value that I choose for x, it doesn't change the 1 or the 4. 1 is never equal to 4. No matter what x I pick, 1 is never equal to 4. This is always false. 1 equals 4. Therefore, this equation, x plus 1 equals x plus 4, is always false. What about this one? This looked a lot more complicated to start with, but it boiled down to, right, this equation. I simplified both sides. That wasn't even really an equation solving step. That was just making each of the expressions on either side look a little nicer. But this kind of transformed into this equation with the same solutions as the original equation. I applied an equation solving step, subtract 10x from both sides. that transforms 10x plus 2 equals 10x plus 6 into another equation, 2 equals 6, that has exactly the same solutions as the previous one, or as the original one. 2 is never equal 6. This is never true. It's false for all values of x. No matter what value of x I pick, 2 is never equal to 6. Therefore, no matter what value of x I pick, 10x plus 2 is never equal to 10x plus 6, or whatever value of x I pick, 5 times 2x minus 1 plus 7 is never equal to 2 times x plus 3 plus 8x. It's impossible to find a value of x that makes these two sides equal. In other words, this equation we would either say has no solutions, or if we wanted to be a little more technical, we might say it's a contradiction. It's internally inconsistent to make this claim. Okay. So this is what we call a contradiction. It's always false for every x. It has no solutions. So even these linear equations we see are a little bit complicated, right? They have some nuances to them. Now let's come back up and take a look at this middle one. 2x plus 2 equals 2 times x plus 1. Remember, my question is, what value or values maybe of x can I substitute in that make this true? Well, I could simplify, I suppose. 2x plus 2 equals, I could distribute on the right. And well, I mean, this just gives me 2x plus 2. I just have a thing equals itself. I have an envelope and 2 more coins on the left balance, and an envelope and 2 more coins on the right balance. What could that envelope weigh and have these scales still balance? The envelope could contain no coins and it would balance, or 10 coins and it would balance, or 100 and it would balance, or maybe a little more abstractly, like -5 coins, it would still balance. Because there's just one envelope on either side and 2 coins on either side, there's exactly the same amount of stuff on either side, regardless of what is in that those envelopes. Of course, the envelopes have the same stuff in them, right? This is the same variable. Or another way I could think about it is I could apply an equation solving step here, subtract 2x, in an attempt to get to combine my variable terms together, but I just get 2 equals 2. Well, this equation, 2 equals 2, has the same solutions as this equation or as the original equation. It is always true. Again, it almost too silly of a question to answer. Is there any value of x that I could choose that would make 2 equals 2 a false statement? Well, of course not. If I choose x equals 0 or 10 or -100, 2 equals 2 is just 2 equals 2. The value of x does not impact the truth of the statement 2 equals 2, which is always true. Therefore, this statement and this statement are always true as well. This is always true for every x. These types of statements that are always true, we call identities. It's essentially just saying that one side is really just a rephrasing of the other side, that we basically said the same thing twice. Instead of saying something like the ball is on the couch or the ball is on the floor, we just said the ball is the ball. It's like, okay, well, yeah, I guess that's true, right? The ball is the ball. Like if I say the ball is on the floor, I look and it might or might not be on the floor. But if I say the ball is the ball, like there's really nothing to argue with, right? So we call this an identity, or we might say that there are infinitely many solutions. Or we might say something like, the solutions are all real numbers or something like that. Or like any value of x is a solution. So is x equals 100 a solution? Yes. Is x equals negative pi a solution? Yes. I mean, we haven't talked about pi yet in this course, but I think it's addressed in MAT090 a little bit. But yeah, x equals negative pi, that's a solution. You know, x equals 37/15, that's a solution. Think of whatever your favorite, number or fraction or decimal is, write it down, that's a solution. That's called an identity. So practically speaking, if I'm ever going through my equation solving steps, and just to bring this point home, if I do my equation solving steps to x plus 1 equals 4, I subtract 1, and I get x equals 3. That's my condition. If I ever do my equation solving steps and do them validly and carefully and do the arithmetic properly and end up with all of my x's going away, I either end up with an equation relating two numbers that is true, that is correct, like 2 equals 2 or 10 equals 10, in which case it's always true. I have an identity. All values of x are solutions. Or if all my x's go away and I end up with a statement like 1 equals 4 or negative 5 equals 25 or something like that, that's not a correct statement. It's always false. I have a contradiction. There are no solutions. Okay, so I think for the purposes of time, I'm gonna cheat a little bit here. We will take these last 5 problems. We have about 7 minutes left. And I'll basically treat them all like exercises so we get some more practice on these. We'll see how many we get through. I think we'll probably get through about 3 of them. But start with this one, start working through it, and I'll kind of work through it alongside you. And we get to about 10:09 or so, we'll stop for today and then probably wrap up a couple of them next time. But start working on these all as exercises, and then we'll touch base in about 5 minutes or so. Okay, I think we'll stop there. Sorry, I kind of rushed through that because I had a technical issue at the beginning. I mistakenly chose the pen that tries to figure out what I'm writing and turn it into printed text, and it usually doesn't do that very well. So uh, I had to mess with that for a minute or so. But yeah, so I think if you got through these three, that would be uh, that would be a really strong result. I think if you got through one or two in that time, I think that's good. Um, but we see the first one is an identity, the second one a contradiction, and the third one a conditional. I suppose I should write that here. The third one, the two sides are the same if and only if t equals -1/2. We come back, we'll do these last two as kind of warm-up exercises, and then move on from there. So that's all I have for today. Let me stop the recording.